In the last section, we talked about Cartesian coordinates, where we had our x and y axes. In this section, we're going to talk about what happens when we have some sort of an equation that relates x values to y values, such as something like x squared minus 3y cubed is equal to x. There are different x and y values, and we can get some information about this equation by looking at its graph. The graph is a set of all points, x and y, where these two values of x and y satisfy this equation. Now, this particular equation is a little tricky to graph by hand, though we will eventually be able to do that in this course. But let's go ahead and graph it in Geogebra. So just go ahead and type this in. I get the powers here by using the caret on Shift 6, by the way, if you haven't seen that before. And we get this particular curve. In fact, most equations are going to give us a curve, where we can just follow along the curve, and it's nice and smooth. Not all equations, but most of them will be similar to this. If we pick a particular point, and if we pick a point that's close to the equation, to this curve, you can kind of see how Geogebra changes the cursor here, and it will plot specifically a point on the curve, and we can see that it represents two numbers here. If we were to take those two numbers and try to plug them into our equation that we're given, we can see what happens. So we have 5.03 and 1.89. We'll go ahead and look at that. So I think it's 8.9, right? Yeah. If we go ahead and plug those into a calculator, we're plugging those into our equation here. We want to see if we plug 5.03 in for this x and 1.89 in for this y, will we get the x, this value, 5.03, out on this side? So we can go ahead and write that out. That is supposed to be a cube. Square that. Minus 3 times times 1.89. That's going to be cubed. And we come out with 5.047. Now, that's not exactly the 5.03 that we have here, but that's just because the values that we've written down here are not actually exact. The GeoGebra is only rounding to 2 decimal places. And so the fact that we even got close, this is only a little bit off from 5.03, means that we can be pretty sure that this is representing an actual point that satisfies this equation. If we picked a point, maybe let's say if we move this around, we might pick, say, here, the point 1, 0. If we plug those values into our equation, we get an exact result. That we get 1 equals 1. But any other point on here, as long as we accept some rounding errors, all these points are going to satisfy our equation. And that's what our graph is supposed to mean. This represents every single point that does satisfy this equation, and maybe we can get some information about the equation from the graph, or vice versa. Now let's pick something a little simpler and try graphing it ourselves without using GeoGebra. So I'm just going to go and pick y equals x squared. This is a nice starter curve or equation that we'll be seeing a lot in this course, just because it's a nice a nice example for a lot of things that we want to do. What does this thing look like? Well, we can start out by making a table of various pairs of numbers that satisfy the equation. I like to put those into a table. In order to actually find these pairs, I'm just going to pick values for one of my variables. In this case, I'm going to pick x because that's the more complicated one here. If I plug a number in for x, we'll see that specific y's will have to be paired up with it. So if I pick x here, put y's here, maybe I can pick something simple for x like 0. If I plug 0 in for this x, what possible values of y can correspond to it? Well, we have y equals 0 squared, which is just 0. That's simple enough. So 0 actually has to pair with 0. It can't pair with anything else. If I put in 1 for x, well, now I have 1 squared. This gives me a 1. If I plug in 2, this time 2 squared gives me a 4. And I can keep going. 3, if I plug in there, 3 squared is 9. I don't have to plug in positive values. I can plug in a negative 1. If I plug negative 1 in here, remember negative 1, the negative is part of the x, it's being squared, and so the negative actually goes away. We get a positive 1. And then we get negative 2 corresponds to 4, negative 3 corresponds to 9, and so on and so forth. Now note, every x value here does have explicitly only one y value that corresponds to it. That's not always going to be true. And it's not true that every y value over here has a unique x that it corresponds to. So 1 corresponds to 1 and negative 1. So we'll get into more of how we can distinguish when there's repeated values and all that later on in the course. But the point here is that we can go ahead and plot these points. So I'm going to go ahead and put my x-axis pretty low down here because I don't have any negative values for my y's. That's one advantage of making a table beforehand is you know what scales you need for your axes here. So we'll have, go ahead and mark out 1, 2, 3, 1, 2, make this a little longer, 3. And I want to be able to get up to 9, so my scale might not be quite correct here, but we'll put 9 up there. I don't know if I want to plot every single one of these. Okay, those are approximately even. So we have 9 tick marks here. So I'll go ahead and plot these points. I've actually already started. I plotted the origin here because 0, 0 is a point on my curve. Now we have 1, 1. That is a point on our curve. 2, 4 is a point on our curve. 3, 9. So 3, 9 is a point on our curve. On the other side, we have negative 1, 1. We have negative 2, 4. And we have negative 3, 9. Now, of course, we're missing infinitely many points. There's a lot of points that we have not plotted. We could add them to our table, but we're never going to get all of the points on the curve. There's uncountably many points on this curve. There's a bunch of points between each of the points that we have plotted, and there's points that are off the page. But we can go ahead and draw a curve that passes through the points that we do have. Now, we'll get better tools as we go through calculus that allow us to figure out where the more interesting stuff happens, so we can plot the curve with more accuracy and all that. But for now, we'll just be satisfied with just drawing a curve that passes through our points, or at least approximately through them. We have a nice little curve there. Now this actually does have a name. This is called a parabola. Yeah. And it turns out in any quadratic, so here y equals x squared is the simplest quadratic that we can have, but any quadratic of the form y equals ax squared plus bx plus c, where a, b, and c are numbers, but we don't want a to not be 0, or else it's a simpler category called a linear equation. But when we have an equation like this, it's called a quadratic. And the graph of any quadratic equation is a parabola. It has this same basic shape, but the a, b, and c's will determine the scale and the location of the parabola. So this could be moved around and shrunken or expanded, all that kind of stuff. And any parabola corresponds to a given quadratic. They're intrinsically linked with each other. Now, just plotting points may not be enough. Here's an example that the book gives us. They've given us a plot of 4 points. These points supposedly came from some equation, and we want to know what the curve is. But without any more information that we have, just these 4 points, how might we draw the curve through those points? Well, there's actually a ton of possibilities. Here are just three possibilities that the book gives us. We could have something that has actually 2 parts to it that just keeps going down to infinity as it gets closer to the y-axis. It could actually be part of a circle, or maybe it is a parabola. Just from having those 4 points, we don't know. Now, if we had the equation in front of us, maybe we'd plot some more points and eliminate a few possibilities. But we can never be 100% certain just from plotting points. But how do we actually deal with that, though? How can we make sure that we have the correct graph, or at least close enough to the correct graph? Well, one way is to just not pick random points. If we look for significant points in the curve, those will give us more information about what the curve has to do. Now, we'll get into more examples of significant points on a curve later on in calculus. Specifically, I think in chapter 4. No, in chapter 3, I believe. We'll actually get into things that we call critical points and inflection points, and we'll get information about how a curve has to behave between such points, things like that. We'll have a lot more tools in the future. But the simplest tool we can talk about right now, the so-called intercepts. Basically, if we have a particular equation, we can find out where the graph of that equation hits the x or y axes. Let's take an example. Y equals x squared minus 1. If we want to know where this hits the x-axis, we get what we call the X-Intercepts. These are where y has to equal 0. Because recall, the points along the x-axis are the points where y equals 0. The y values cannot be anything other than 0. But the x values can be whatever we want them to be. So we'd go ahead and replace the y here with a 0. And we would solve for what x values will work. Now here, this is simple enough. We do have to actually take the square root eventually, but we can bring the 1 over. So we have x squared equals 1, and then x is equal to, well, it could be 1, or it could be a negative 1. Don't forget your negatives when you're taking the square root. And so our x-intercepts, well, there's 2 possibilities here. There's 1, 0, and there's negative 1, 0. Those are 2 points where this curve actually hits the x-axis. In fact, those are the only 2 points. We cannot hit the x-axis anywhere else. And that can actually be relevant for helping us graph things as well. If we look for the y-intercepts, Now, just like this was where y equals 0, y-intercepts are where x equals 0. So if we plug in 0 for our x here, what values of y do we get? Well, here we have y is equal to 0 squared minus 1, which is just negative 1. And so we only have 1 point this time. We have 0, x equals 0, and we have a negative 1. And so if we were to plot this particular curve, we would know, let's draw it over here. We know it has to hit the y-axis at 0, negative 1, so we go down 1 on the y-axis. And it has to hit the x-axis at 1 and negative 1. So we'll go 1 either direction on the x-axis. Now, of course, this doesn't give us all the information about our graph. And if we looked a little harder and used some techniques from calculus, we could definitely get a lot more information. But we do kind of get the idea that our graph is going to look something like this. We can't have, say, a circle because we can't have this close up because we'd have to hit the y-axis again. So we eliminate a lot of possibilities because we know both some points on the graph and some points that are not on the graph. We actually know no other point on our axes can be on that graph, and that gives us a lot of information about our curve. And that's very useful for us. Let's look at another example of finding the intercepts of a curve. Let's look at problem 29. Here we have y is equal to x squared minus 4 divided by x minus 2. Now, right off the bat, we don't really know what this looks like. We'd have to do some work to figure that out. But at least we can try to find the intercepts. Let's look for x-intercepts first. Remember here, the x-intercepts are where y equals 0. So we're going to put in 0 for y, and then we'll try to solve for x. Now notice that we have a fraction here. A fraction can only equal 0 if the numerator equals 0 and the denominator is not 0. So here, we'll go ahead and turn this into the equation 0 equals x squared minus 4. We might have to come back and see if the bottom actually becomes 0 with whatever solutions we get here. But if 0 equals x squared minus 4, we can go ahead and move the 4 over to this other side. Write that as x squared equals 4. If we take the square root, we have x equals, well, 2 is a possibility, but also negative 2 is a possibility. But if we look at what numbers we have here, if we're going to just take 2, when we plug in here, we get 2 minus 2 on the bottom. We have 0 on the bottom. That's a problem. We have to exclude the positive 2. So our only possibility here is going to be negative 2, 0. That's our only possible x-intercept. What about y-intercept? Well, this time x is equal to 0. So if y is equal to 0 squared minus 4 divided by 0 minus 2. We just have to figure out what this is. Well, we can basically just exclude those. We have negative 4 and a negative 2. If we divide negative 4 by negative 2, we get a 2. And that means we do have a y-intercept of 0, 2. And if we go ahead and actually plot this curve, so our curve was y is equal to x squared minus 4 divided by x minus 2. We can see that, well, it looks like a line. It actually turns out it is mostly a line, but that takes a little bit of work to show. But the point here is that we know it hit at negative 2, 0 and at 0, 2. That's where it hits our axes, and it doesn't hit anywhere else. And notice that when we excluded x equals 2, that is not an intercept on our curve. It looks like we have 2, 4 is a point on our curve. Now, technically, it's not there. Technically, there's a little hole here. If I were to draw this by hand, I would draw it something like... I'd leave a little hole there at 2. Because I can't plug 2 into my equation here. So that can't be there can't be a point on the curve where x equals 2. Okay? Now sometimes we have multiple equations or multiple graphs, and we want to see how they might interact with each other. Let's say we have two curves, or two equations. We'll start with the equations here. Y is equal to x squared minus 4, and y is equal to x plus 2. These two represent two different graphs, and we want to see how they interact. Let's go ahead and just plot them. Oops. We have y is equal to x squared minus 4. And we have y is equal to x plus 2. We have two different graphs here. And we can see that these two graphs intersect in 2 points. There's 2 points, 2 pairs of numbers that satisfy both equations at the exact same time. Now, we might be able to guess what those are on this particular graph, but if we had something more complicated here, we'd have to solve the two equations together in order to figure out what points those are. Of course, how difficult it is to actually find the points of intersection does depend on the complexity of our equations. But when we have these nice simple equations where we have y equals some equation in terms of x, some formula in terms of x, then it actually is not too hard. Because we know the y values have to be the same thing, and so whatever we have equal to that y also have to be the same thing. So we essentially get to set the two equations, or the two formulas in x equal to each other. You have x squared minus 4 is equal to x plus 2. So if we solve this for x, we do have to recall how we solve a quadratic from algebra. I'm going to move everything to one side. So we have x squared, we have a minus x, and now the minus 4 will combine with a negative 2. Should actually combine them. And we're left with a 0 on this side. Now, we might have to use the quadratic formula in a more complicated situation, but this one can actually be factored. We can factor this as x minus 3 and x plus 2. And that means, because if we have a product equaling 0, one of the two factors has to be 0. And so x either has to be a 3 or it has to be a negative 2. I'll put that one first just because the smaller number. Now, of course, these are only the x values. We do need to know what the y values are that correspond to these x values. And we need to do that for both of these two values. So when x equals 2, negative 2, I need to find out what y value corresponds to that negative 2. But because we found these by saying that these two expressions, the x squared minus 4 and the x plus 2, give us the same y value when we plug in negative 2, I can choose either one of these to plug the negative 2 into. I'm going to pick the simpler one, y equals x plus 2. So if x is equal to negative 2, I plug in negative 2 for that x. So negative 2 plus 2 gives me a 0. So we get the point, negative 2, 0, that satisfies both these two equations. Now, you might want to check to make sure that the negative 2, 0 does satisfy the other equation. In some situations, you can get some, what we call extraneous roots or extraneous solutions. It always helps to check your work. So if I plug in negative 2, 0 into here, well, 0 equals negative 2 squared is 4, minus 4. We get 0 equals 0. When we set x equals to 3, since we haven't dealt with this last one here, again, we can use either one of our equations. And I'm going to use the x plus 2 again. So I'll go ahead and plug in 3. We still have the plus 2, and we get a 5. So the point 3, 5 should be another point of intersection. And you can check it in y equals x squared minus 4. I'm going to leave that up to you to do. But if we go ahead and actually plot those points, we have a point A that definitely looks like it's an intersection point. And we have 3, 5 is our point B. That also looks like it's one of our intersection points. So it's that simple. We only have to solve the equations together. Whether or not that part is simple is depends on the situation. For a more complicated example, let's look at problem 47. Here we have two equations. We have y is equal to x to the fourth minus 2x squared plus 1. And we have y is equal to 1 minus x squared. If we go ahead and plot those two curves, so we had y is equal to x to the fourth minus 2x squared plus 1. Fairly complicated looking graph there. It's got some interesting things to it. Then we also have y is equal to 1 minus x squared. Now that is a quadratic, so we did get a parabola like we would expect. And if we kind of zoom in here, we can kind of see that, well, we definitely have two crossing points here. And it looks like we might have them touching there. So we might have an intersection point there as well. Let's see if we can actually find those and show that they exist just using some algebra. So recall, when we're looking for intersection points, when we have this nice y equals a formula in terms of x, for both of them, all we have to do is set them equal to each other to find out what x values work. Now, of course, this time we do need to solve this equation that has an x to the fourth in it. Hopefully things work out nicely. Of course, they wouldn't give you one that didn't work out nicely, but in the real world, you might come across ones where you might have some trouble solving it. So what do? We're going to move everything to one side. So leave the x to the fourth here. I have a negative 2x squared. I'll add an x squared to that, which will actually make that into a negative x squared. We have a plus 1 actually on both sides. We'll cancel those 1s on both sides. And we're just left with x to the fourth minus x squared is equal to 0. Now there's a couple ways you could approach this. I'll go ahead and actually factor out an x squared. I'm going to pull an x squared out of this side. When I pull x squared out of the x to the fourth, I'm left with an x squared. Obviously, if I pull x squared out of the x squared, I just get a 1, so I get a minus 1 here. Now, this is nice and factor. We could actually factor it a little bit more. X squared minus 1 can actually factor as x minus 1 and x plus 1. And the fact that this product is equal to 0 means that one of these factors has to equal 0. We could have x is equal to 0. We could have x is equal to 1. Or we could have x is equal to negative 1. Those are the possibilities. Now, I do need to figure out what particular y values correspond to those. If x equals 0, that means that when I plug it into either one of these, and I'll go ahead and pick the y is equal to 1 minus x squared, because it is the simpler of the two. But if I plug it into either one of these, I should get the same answer. And it might be helpful to check your work by plugging it into both of them, just to be sure. So I have y is equal to 1 minus 0 squared, or 1. So you have the point 0, 1. If I put in x equals, let's just do the 1 first. Then y is equal to 1 minus 1 squared. Well, 1 minus 1 is 0, and so we get the point 1, 0. Finally, when x equals negative 1, very similar. Y is equal to 1 minus, this time, negative 1 squared. But the square just turns that into a positive 1. So we still have 1 minus 1, or 0. So negative 1, 0 should also be an intersection point. And you can plug those into this one here, and you should get the same result. And that agrees with what we have here. We can definitely believe that 1, 0 and negative 1, 0 are both intersection points. And then up here at 0, 1, that was the other one. Alright, so there is definitely more to talk about in this section, and we'll get to that. But I don't want to have a single massive huge video, so I'm going to split this up into multiple videos. I'll be doing that frequently throughout the semester. It'll just depend on how much content we have to get through. So I'll see you guys in the next video.